Okay, let's now try to finish the composite pattern. Okay, that's the first job. And then we talk about some continuation topic of composite, which is something also very interesting called visitor pattern. Okay, let's understand composite first before we get to visitor. Let's just review the kind of design problem we are facing. Basically, every time when the problem you're facing here, you can model them using some tree structure with a hierarchy. That means you can use a composite pattern. Okay, so now let's see just see the problem itself, and then let's try to categorize the modeling artifacts we have to pay attention to. At the top level there, you got some cabinets over here, and then at the second level, you got chassis over here. You got two chassis, and then under chassis, you got cart. You can see cart in some way is fundamentally different from chassis, because chassis can contain other modeling components, but cart cannot. Right? So we call chassis something called recursive cases, which means they might develop even further. But for card, hard drive, or DVD, CD-ROM, so these are the basic modeling component. You cannot just build any further. So these are the leaves of the trees. On the other hand, the composite or the recursive components there, they are the nodes on the tree. Okay? That's just for this particular example. So this is kind of problem we are facing with. Okay? And we'll see more example when we get to the visitor pattern to start from there. Okay? Okay, so now, the challenge is there are two categories of modeling components. One is called base, and the other one is called recursive. Let's see how we can do some computation over here. Let's say for every equipment, like a cabinet, chassis, card, hard drive, DVD, ROM, etc., they got some price over here. For example, let's say this power supply, 100 bucks, and DVD ROM, let's say every component is 100 bucks. And only the basic one, let's say power supply, DVD ROM, hard drive, and card, 100 bucks each. Let's say I want to know what's the value for this particular cabinets. How can I figure out its price? In this case, we have to somehow recursively to go through every component in the tree and then to aggregate their prices, right? So that's kind of the computation what you would like to do. And not just price, or it can be power consumption, or you want to make some conclusion out of the tree, right? We'll see that another example from another extreme in the visitor pattern. Okay, that's a problem we are facing with. Any question about base and recursive, the concept over here? Again, chassis, cabinets, these are recursive equipments. And power supply, DVD drive, hard drive, and card, they are basic. Okay, so now let's go on. I will go through this slide last because this one here summarizes how polymorphism dynamic binding work for composite pattern. You wouldn't appreciate it so much before we see the architecture. So let me skip this slide just for now. I'll go back here in just a moment. Let's see some design over here, okay? So this is a first design, okay? You can see that, let's just see the first design. Let's see if we can criticize about it or you think that's good enough. Okay, let me just go to iPad over here, the same diagram. So what we have is here. So now think of, let's see where the client is. So this is the client, just the main program. And we have some client-supplier relationship over here, and the client declares some attribute called E of type equipments. And the equipment itself can be like a tree. It can be cabinets, inside which you got chassis, inside which we got bus and card and etc. Okay. Let's see how the inheritance hierarchy here is going on. It's working here. So you can see at the top level we have a deferred class called equipments over here, and then we have different equipment classes. We got card, we got disk drive, and we got cabinets, chassis, bus, and etc. We also get something called composite equipments over here. Okay, that's what we have. So far, so good. Now, I want you to pay attention to several things over here. You can see that over here, we have at the equipment level, there is a common query, or remember the uniform access principle. That means when we define price over here, that means it can either be implemented as an attribute or a query. So we don't know yet which one we're going. That's not important. Now, I want you to focus on these two features. Let me use this color here. Add and children. Okay? The reason that we have these two features here is for the composite equipments, because we know that the composite equipment is a descending class of the equipment over here. That's why we want to make sure, let's say for cabinets, let's just go back to the previous, let's say diagram here. For cabinet over here, we want to be able to add different child into itself. For example, we want to add a child called chassis, add another child of type chassis, another child of type card. For example, that's kind of the thing we want to support. That is why you got add and also children over here. And children is simply just a list of equipments, or it can be array, doesn't matter, just a collection. And also you got add here, simply take a single equipment. You can see over here, again, equipment is the static type of the parameter, which means any objects whose dynamic type is a descendant class of equipments can be added, including everything, right? That's under equipments over here, okay? And one more thing to mention before we can try to criticize this design over here. And another thing we have over here is you can see for the composite equipment class over here, we also have a client-supply relationship. So we are emphasizing that for every composite equipment, because we inherit the children feature over here. So that means we are really making some client supplier. For example, let's say over here, let's say for cabinets over here, you can think of, so cabinet here, so we got children, and then in this case, it has 3 children. The first child, so this is children at position 1, this is at position 2, this is at position 3. So each one of them, we have some client supplier, right? So we are making use of other classes, okay? That's why you got this client supplier relation here. Now, this is our first design for the composite, which means whenever we got some tree structure problem to solve, this is our first attempt of the design. Can you see any drawback for that before I give you any hints? Typically, just before you say anything, typically when we say drawback, think more about if your design smelts, that's kind of criteria, or if you violate single choice principle, things like that. Yes, go ahead.
Why the children fund to the parents composite equipment?
Why would that be a drawback? So basically you were criticizing about this error over here, right? Why would that be? It says client supplier. So first of all, let's understand what this error means. That simply means in the composite equipments here, we have some attributes, children of type, a list of equipments. That's what we have. See, actually, in some way that makes sense because, for example, you can see over here, cabinets is a composite equipment. It has a children list of size 3. First one being chassis, second one chassis, third one being a card. Each one of them is a descendant class of equipments. So this part here actually makes sense. Anybody else? Yes, go ahead. Very good. Let me just rephrase that. That's exactly the issue. Okay, so now let's see what the main drawback for this design. I'll just repeat exactly what you said. Think about this. Where did we define the composite only features over here? You can see add and children over here. So these are composite, or you can say recursive case specific features. So where do we put that? We put them in the common class of the recursive and base cases, right? Because we put them inside the equipment class, which means both the add and children, they will be inherited to every descendant class, including, for example, card. So now, in the card class, you got children, you got add child. Does that make any real sense? No. It wouldn't, because for the car, it's a basic equipment. You can never have add any more component into the child, right? In the tree, for example, you cannot have anything like this. Let's say card contains just another card, or card contains another cabinets, right? It simply doesn't make sense. That should not be allowed. So if you actually somehow allow add and children over here, that's actually polluting the interface for every descendant class, because these two features are only applicable for composite, but not for base cases. Okay? Let me give you another analogy. think about the example we did before. Remember we got students, and also we got resident students, also we got non-resident students. What would happen if we try to declare the two features, premium rates and discount rate, at the student level? In that case, all the descendant classes will be forced to inherit all the features in the superclass. In that case, discount rate will be inherited to the resident students. That doesn't make sense. Similarly, the premium rate will also be inherited to the non-resident students. Also doesn't make sense. Okay? So we got exactly this kind of dilemma over here. You're inheriting way too much features in some classes, so you shouldn't really put add and children inside this common equipment class. That's a drawback. Okay? Any question about this design here? That's the first attempt. It's not too bad, but you do have cases where it simply doesn't make sense. Okay? For composite, it was okay, but it doesn't really apply in general to every kind of equipment. Okay. Now, how can we improve this? The way to improve this is we want to make add and children specific to composite equipments. That's what we want to do. And how do we do that? Let me show you the new design over here. That's a new design. Okay. Let me just go back here so you can read through the slides. I also got an annotation here for you. You can read it over in the slides. Okay. So now let's see this better design over here. The main changes is as follows. First of all, we have the composite equipments is still a descendant of equipments. But now we have something called multiple inheritance. Okay, I'll just write it here. Multiple inheritance. The way you can think of multiple inheritance in IFO is like you can implement from multiple interfaces in Java. So you're really inheriting signature or inheriting code. But in the case of IFO, as long as you don't have any name clashes, you can always inherit from as many classes as you like. Okay? We wouldn't cover so much about multiple inheritance. This might be the only pattern, but just make sure you understand this particular example. So here you can see that composite equipment also inherits from composite, just a separate class. So now, take a guess. Where should we define the add and also children features? We say that it was not a good idea to define them in equipments. Now we do have a separate class over here, right? So why don't we define them over there? So you will see that over here, we will put add and also children over there, which means these two features are only inherited to composite and also its descendants. These only. They will not be inherited to the basic one, like a car and disk drive. So we are really having separate interfaces. One for base cases and the other one for recursive cases. Any question about this particular design over here? Yes, go ahead. No, you don't. You don't. So now in this design, what do you have in the equipment? Let's try to figure that out. I will also show you some code in just a moment. In this case, in equipment, we only get things like price, which means for any equipment, and the equipment might either be basic or recursive. The only thing we want to know about it is figure out the price. If the equipment is simply like a memory card, tell me the unit price of that. If the equipment happens to be like a composite, let's say cabinets, tell me the value of it by aggregating all the values of its subcomponents, right? And now, the fact that we actually make the composite equipments the descendant class of composite over here, that means only this branch over here is going to inherit add and children over here. Guys, any question about this better design over here? But you should really see why. Yes?
Do we have a feature of add children in composite or do we have it in composite?
Good question. So here, the composite class over there is actually a very general class. So we simply have to add and children over there. You can see, I'll give you more detail when we see the code. You can see that composite over there takes a T. T, that means it's generic. So now we are trying to make the composite not just usable for this particular equipment's problem here. once you define this composite class over here, it can be reused for other problems as well, because that's generic. It can be composite of equipment, composite of students, or composite of expression, as we'll see in the visitor lecture. Yeah.
So for the green arrow of the children, is
Uh-huh.
only to the composite, not the equipment?
No, I tell you why. It's a good question. The question was, what about this green arrow here? I know that's a usual confusion. Remember what the green arrow really means. I'll try to be consistent with color. This is the green arrow we have. Remember, red arrows are about inheritance. The green arrows are about client supplier. So if you have, let me just give you a large view of that already here. Let's say I have composite equipments over here. Let's say this is a class I have, and then I have the green arrow over here. And then let me just draw that over here. And then that's actually the equipments. Okay? And this is a plus, that's star, and then we got equipments. And then I have something here called children, and then of type list. And then I have dot, dot, dot. So dot, dot, dot here simply means it corresponds to the type of the client's, of where the client supplier arrow is pointing to. So that means it's a list of equipments. So what does this client supplier relationship really means? It means that in the composite equipments class, we are trying to use the surface of the equipments. And the way we use it is by declaring an attributes list of equipments. Okay? To be more precise, that means you must have something like this. Class, that was a composite equipment over here for short, and then end. And so we must have a feature over here, which is children. And then here we have list of equipments. Okay, let me just draw some connection here. So you can see equipment here, star, and also equipment here. Okay. Does that answer your question, maybe? Okay, so don't get confused with the client-supplier and the inheritance. Typically, you have a client-supplier relationship if you declare attributes or parameters or return types. And inheritance is when you inherit specifically, explicitly from some classes. Okay, so they're different. So they're different. They have different architectural meanings. Okay, you should know both. Guys, any question about this pattern here? So the way I chose to discuss this pattern here is show you the architecture first before I show you the code. Okay. Yes. Go ahead. Okay, you know what? That's another good question here. The question was, what about the dot, dot, dot? Let me try to answer it in a little bit more detailed way. Uh-huh. Okay, let's say this, yes. So what I didn't really put here is class composite equipment, I should say inherits, is part of the declaration, right? Inherits composite. Remember, composite itself is simply just generic, T. Now I want to instantiate to say for this particular composite I'm talking about, it's a composite of equipments, right? So I'm going to put equipment over here. Okay, guys, that makes sense? Okay, so you can see the composite pattern itself is not that complicated. We're just trying to model both the base and the recursive elements. But now we gotta really combine client supplier and inheritance. Okay? Okay? Question? Go ahead.
Why not just add the add children method to composite equipment?
That's a good question. The question was, why not simply, let's say the question was, why don't we simply just get rid of this particular part, right? Get rid of that, and simply put add and children over here, right? If this is the only composite problem we are solving, you're right. It can save you one class. However, later on, let's say this is one problem, which is about the equipment's problem. Let's say we have another similar problem which can also be solved by using the composite pattern. In which case, by using your solution, we also need to have another, let's say, composite students in that case. In the composite student, we also need to have add and children. In that case, we have repetition, which means you design against smells, right? So this is really for reusability, okay? Okay, let me just make a note here. So this part is reusable for any other composite problem. Okay, good. Hopefully that's understandable, right? Good. Guys, any more questions, please? Yeah, go ahead.
So composite design is usually made for that we're absolutely sure this is how we're going to leave it at because it won't support extensibility after we set the card.
Ah, that's a good question. The question was, let's say, apparently there's a big assumption over here. We kind of know the modeling components we have over here. Cabinets, disk drive, card, and also chassis, etc. We pretty much know the hierarchy structure here already, which means later on, what about we want to add some modeling component here? I'll save that question for a little bit later, because you're basically talking about, is this structure here stable over here? Let's assume it's simply stable. So the way we create a tree structure is based on what are the available components you have, and then we simply do that. And of course, later on, let's say if you want to add a new class, for example, let's say if we want to add a new base component, how do we do that? What we're going to do is add a new class, for example, RAM. Let's say there's a basic components. Simply add it as a descending class over here. That's one way to do it. And let's say we got another composite, for example, it's called box. In that case, we can just add another class over here and call it box. Right? That's how we add it. That's how we extend. But things may not be this easy as we talk about the visitor pattern. We'll show you. Okay? Let's save that. Okay. Any more question about composite? Okay? Hopefully it's not too difficult. Okay? Okay, very good. Let's go back there. So that's the okay, the flaw for the first design is you can just read it over. Basically, about the first design, you simply just inherit the add and children into the base components level, which is not good. That's why we got a composite pattern. Okay, so this is a better pattern that we have. Okay, you can also see the annotated page over here, so you will see more explanation. Okay. Okay, let's see some code very quickly. You can also play with the source code I've made available to you on the lectures page. First of all, let's say for the equipments, the reason that we make equipments differ is because the feature we would like to support is called price for now. We simply don't know at the equipment's level how we can compute its price. We simply don't know because it could be the unit price for some memory card, it can be the unit price for some DVD drive, or it can be the composite price for some cabinets. We simply don't know. We just cannot decide. We're going to delay that decision until the descending classes. Okay, that's why we make it deferred. Let's say we only have two generic features. I shouldn't say generic. Some general features, name and price. Now, here I simply put a uniform access principle over here simply because just by looking at the interface of this class, you have no idea how we're going to implement price in the descending classes. It can be attributes or it can be queries. You will see that this principle here exercised very thoroughly in this pattern here. You will see. Let's just define one basic components. For example, you can say card inherits equipments, right? Remember the diagram over here. Over here we say card inherits equipments, okay? And then how do we set the price? There's no need to aggregate the prices for card because it has just itself. In that case, we can simply say, as part of the constructor over here, we simply pass the price. And then we are treating price as an attribute. Okay? That's for the basic components. Okay? Should be no question, right? Up to now. The more interesting bit is about how we can define the recursive equipment. Let's see how we can do that. First of all, let's define the composite. First of all, the composite So the reason that we have this extra class here in this case is for reusability for later problems. So once you define this composite class over here, you can always reuse it for any composite solution. Again, it's deferred, and then we just have some code over here to be shared. So children is of type, let's say linked list of T. And then also we have add child and then just extend. So here you can see polymorphism because once we instantiate a T, for example, T can be instantiated using equipments. Then at the runtime, any objects that is descendant class of equipments can be added. So that's polymorphism. And for reusability, we can also instantiate T by students. In that case, at the runtime, any objects whose dynamic type is a descendant class of students can also be added. Okay? Oh, I thought the door was open. Okay, very good. Now, some very simple exercise for you. That should be very trivial. How do you make the composite class iterable? Okay, how about this? First of all, you gotta, you know the answer, right? Okay, let me, go ahead. How about just handle your question first and then come back iterable? Yeah. You can undefined feature. I would say for the purpose of this course here, we don't really use undefined that often. So I would say typically you redefine or rename. Yeah, I would say usually just reuse, rename, and redefine. If you, let's say here, so undefined, I believe is a keyword in iPhone. If you let's say something very simple. Let's say this. Remember students, example we talked about. Let's say there is a register method in the student class. And then in the subclass over there, we say undefined. We say resident students inherit students undefined register. So that means we no longer want to make the register method available on the students, on the resident students. So what does that mean? That means if you're given a static type of resident students, you can no longer call register anymore because it has been undefined. It's been taken out from that particular static type. Okay. I wouldn't cover too deep on that, but if you want to discuss, we can discuss offline. Okay. Now, guys, what about iterable? First of all, of course, you're going to say composite inherits from iterable of T, let's say. Now, you got to define a new feature, right? Called new cursor. Do you need a new class for that? Do you need to create a new class? How would you do? Oh yeah, exactly. You can simply say result is assigned to children.newCursor because linked list is a collection class is guaranteed to be iterable. So the new cursor is guaranteed to be available. Okay, just to double check your understanding. Very good. Okay, that's about the composite, and let's go on to the next one. Okay. Now we have composite equipments. Now let's remember what the architecture says. The composite equipments inherits from two classes. First is the equipments. The other one is the composite. Two things. Okay. Let's now see how it looks like. Inherits, first of all, equipments over here, and also composite with the T instantiated using equipments. Okay. So also good. Okay. Let's say this. I'm just making up some example. Let's say we are solving another problem, also can be applied for the composite pattern. Let's say it's simply called composite students, for example, composite students. And then we can say inherits students, and then we can say inherits composite of type students. In that case, we are really reusing the same composite generic class. We are not really creating any new classes, like the question you asked before, right? Okay, two classes. And then in the constructor over here, if you just recall very briefly, in the case of the card, the basic components class, in the constructor, we have to pass the price, the unit price, because we treat the price as an attribute. But now in this case, we don't, because we don't have any unit price for composite equipment, let's say. We only aggregate the prices for its components. So that's why we don't really have any price over here. So what we do instead is we say that we have a price query over here. Again, it's uniform access principle. At the equipment level, price, you cannot tell whether it's an attributes or query. But now, in the basic components, we treat it as attributes. In the composite components, we treat it as query. So we can run a loop to go over. Okay, you can see we simply sum up the net prices of all the subcomponents. So what do we do? Remember, because this composite equipment inherits from composite, so there is a feature called children. So children is going to be of type linked list of equipments. So we can simply just call it as follows. We can say across the children as some cursor, and then can you see how dynamic binding is working in this line over here? Hopefully you can see that, right? Let's try, okay? If you look at this code here, first of all, you can see that back to the composite, okay? First of all, you can see the children is going to be linked list of T. And now, in the case of the composite equipments, we instantiate T to be equipments. That means the static type for every element we store in the composite is of static type equipments. Now, the dynamic type can be any modeling components that's in the descendant classes over here. It can be card, can be disk drive, can be cabinets, can be chassis, bus, etc. Right? So now, when you call this particular cursor.item.price, depending on what's the dynamic type that you're calling on. If that's basic, it will simply give you the attribute unit price. If that's composite, it's going to run the loop and figure out what they are. We'll see one example in just a moment, but do you actually understand up to this point what we are saying over here? You can see the query itself is very simple. We simply the cursor.item.price, but you should know that at the runtime, different versions of the price is going to be called different. Okay? Guys, questions? No? Are we good? Sure? Okay, very good. Yes.
Composite price of chassis and loop over somehow. How does that happen?
You mean concrete example? How about just bear with me? The last slide will be example. Let's save that question. Okay, we'll get there. Okay. The question was, can we see some concrete example? Yes, we will in just a moment. Okay. I just want to make sure you understand how we define the code, and then we'll get there. Okay. Okay, let's see some test cases. Okay. Let's go over the code first, and I will show you exactly how it is run. Okay. Let's see the code first. Let's say we have test case over here. First of all, let's pay attention to the types over here. Car and drive, they are of type equipments, okay? Static type. Cabinets is of type cabinets. Question for you. If you compare card and cabinets based on their static type, is there any feature that you can call on cabinets, but you cannot call on card? Any feature based on what we learned? I give you visual hints. Let me repeat the question again, and then I'll show you the diagram. Is there any feature that we can call on cabinets, but we cannot call the same feature on card or drive? Hints, diagram, any feature. Anyone other than do some? Okay, go ahead. Add child and children, right? Because the static type tells you the method or features you can call. In this case, for card and drive, they are of static type equipments, which means only the features defined in this equipment you can call, which is only price and name as we define. But now the cabinet is of type composite, or actually just even here. In that case, we do inherit the children from the composite, right? So just notice that, okay? You will see that. Okay, and then we also got chassis over here, and then let's see how we can build the composite, okay? Let's see the code, and I will show you how you can visualize it, okay? It's not too bad. The way you visualize it is by using a tree. First of all, let's say we create a new card instance, 16 megabyte token ring, and then 200 bahts, for example, unit price. You only give the unit price for basic components. And then you got this drive, and then 500 gigabytes hard drive, and then 500 bahts. And also now you can see that bus over here is a composite equipment. So it does not have a unit price anymore. That's our convention. Okay. Of course, you can make it have a unit price if you want to. Okay. And then we also get we also got two chassis. You got PC chassis and PC, oh sorry, only one chassis and one cabinets. One PC chassis and one PC cabinets. So these are what we have. Let's see how we can connect them together. Okay. Let's see this. First of all, we say bus.add. Let's try to build up the tree right away. Okay. Let me just go back to iPad. Let me just add a new page over here. Okay. Okay, the first thing we do is we say bus.add. So bus.add some card. Okay. So bus contains some card. Okay, conceptually. Okay. And then what about the next line? Chassis.add bus. Chassis.add bus, which means the bus, which contains the card, is now part of the components for chassis. Okay. Next one. Also, we have chassis.add drive. Okay. Now chassis, which got another one, which is a drive, which is itself basic. And then we have another thing, which is cabinets.add chassis. Now what we do is cabinets.add chassis, right? Okay, it's one of its children. And now what we got is cabinets.price 700. How does that work? Okay, let's see that. So how do we calculate that? It's actually 700, 200, and 500, okay? Let me just put in the price first. We set the price for card is 200. And the drive over here is 700. And the feature call over here is asking, what's cabinet price? Okay? So we're asking, what's cabinet price? That's the question we're asking. Okay? Remember the code you should really look at. Let me just go back there very quickly. The way you do that is by across all the children of this particular cabinets or composite components, and then call the price feature on each of its children. Okay? In this case, what do we do? You can see over here, how many children do we have for this particular cabinets? Only one. So we're going to call chassis.price. In which case, is it going to return a value right away, or it is going to do some further processing? Further, right? In this case, it has two children, child number 1 and child number 2. So price, I'll put a question mark for now because we don't know yet. It's a bit like a recursion, basically, right? And now, for child number 1, so I would say child number 1. So this is child number 2. Now, how can we figure out the child number 1's price? Do we know that right away? No, we got to figure out for all his children, right? In this case, bus got only one child. In which case, we got to figure out the price for the card, which we know right away, right? So now we're going to return. Price is going to be just 200 for the bus. And then we're going to figure out what's the price for the drive. Do we know that right away? We do. Oh. It's really bad, right? Okay, I don't know who that person is. Anyway, could be my mom, actually. Anyway, never mind. Okay, now over here, so do we know the price for drive right away? We do, because it's a unit price, right? It's a basic one. So now, how do we figure out the chassis price? In which case, we're going to accumulate the prices for each of these children, which would be 200 plus 700, which means we get 700. And then finally, what's the price for cabinets? Depends on what the sum up price is for all its children. In this case, only the chassis, the only child. So that will be 700. Final answer. Guys, any question over here? I know it's a little bit fast, but if you really want me to repeat, that's okay, but just let me know if you're okay. Go ahead. Which one? What about the...
You know in chassis, right? We have less, right?
Yeah.
So why don't take 700 plus 100?
No. We're talking about aggregate prices, right? So somehow you can think of Think of this. So in our particular example over here, only the base components have their values, only them. Okay, so which means you got card, you got only card and drive. So these are the only leaves that actually matter. In which case, you should really aggregate 200 and 700 eventually, right? But now, your question was, why don't we also add up the 200 here and 700 here? No, then that means you are double counting, right? Yeah, guys, do you see what the question was? The question was, when we add up the 200 plus 500, why don't we add up the intermediate calculations over here, which is the bus value is about 200, and the chassis value over here is 700. Why don't we add up 700 plus 200? No, you are calculating it wrongly, right? Only the, let me just draw one more diagram, otherwise you will just get confused, right? Let me just give you one more example. Let's say we got this, cabinets, chassis, chassis, chassis. Let's say this one we got bus, and then we have drive. Actually, it doesn't make sense. That's a cart. And the chassis over here also get chassis, chassis, and then power supply. Oh, actually, just use cart. Drive, and also drive. This one just drive. Okay, so now, let's say I ask you the top question there. What is cabinets dot price? What is that? So let's figure out just from the diagram and see how that will work out. We know that the cart has the price 200. Drive is 500. This one, 500. And this one here, 500. So these are the leaf components. So eventually the answer you should get will be 700 plus 1,000 will be 1,700, right? So this is the eventual answer. But how is that calculated using this kind of tree structure? Let's go over that very quickly again, okay? Let's try. Let's say this, if I simply say what is the price at the top level over here, if I cannot know it right away because that's composite components, I need to figure out from adding up the individual components for that particular composite, right? So now, child number 1, child number 2, child number 3. What's the price for that? What is the price for that? And what is the price for that? Once I can get these 3 prices, I can add them up together, right? But now, do I know them right away? I don't, because they're composite. In that case, I'll simply just go to the children, right? For this particular chassis, it has only one child. What's its price? I don't know either. I don't know yet, because that's also composite. And then I'll just go to its first child. What's this price? 200. And then there's only one child, so this will just be 200. Okay, and then similarly, this will also be 500. This will be 500, right? And then now, what will be the price for this particular chassis? 200, right? You just have to add up for all the children, but there's only one child. So this will be just 200. And you can see that we already figured out one of the 3 prices we require. Okay, let's go on very quickly. And now you can see what will be the price for the second chassis. 1,000, very good, thank you. And that's the second price we need. And then finally, you can see that for this one over here, that's simply just the drive itself, right? Just 500, okay? And you will simply add up these 3 numbers, which will give you 1,700, okay? Don't double count. That's a good misconception, but it's not right. Duzan, does that answer your question over here? Okay, so I would say, yeah, let me just make a short remark. So I think that it's most important to understand how the same feature is treated differently on a composite tree over here, depending on if you are talking about if the dynamic type is a composite or the dynamic type is a basic one. If it is basic one, you simply return an attribute value. If it's a composite one, you have to go through some routine query computation process, in which case you gotta wait until the aggregation has been completed, and then you can figure out the addition, so summation. Yes, go ahead. Of course, the previous one. This one here?
So my chassis here is 700, with children are 200, and the driver set price 700.
Let me see. Okay. Oh, actually, yeah. Actually, very good. There was a not really typo. This something I wrote wrong, because the drive over here is not 700. It should be 500. I like that. Thank you. If you rewatch the recording, you will see the corrected version. Good. Yeah. Very good. Guys, any more questions? Okay. Now, one more slide I want to do. Now that we understand how the polymorphism dynamic binding is now working, I can now go to the one slide that will summarize the composite pattern. Okay? One more thing to show you, since now we're here. Okay? Let's see, for this one is less messier. Okay? Now, let's say this. From the client's point of view, when the client say cabinets dot price versus bus, let's say versus card dot price. You can see that for both feature costs from the client's point of view, we are calling the same feature. And the client does not have to know that it's actually undergoing some different computations over here. Because for cabinet.price, what we are actually doing is to go through the loop to figure out what's the summation of the children's prices. On the other hand, from card.price, we simply return what's the unit price stored in the attribute for card. Right? From the client's point of view, they're calling the same feature. It makes no difference to them. But you should know that from you as a modeler or implementer's point of view, it's different. Okay? Now, let me just go through that slide, and then we are done with composite. And then we'll go to visitor. Okay? Let's go to that slide over there. Okay, let's summarize what composite pattern is. First of all, when you try to do your design for composite, you should categorize your artifacts, let's say card, power supply, drive, and cabinets, chassis, etc., into two different categories, base and recursive, or base and composite. Okay? Now, what about when you do programming? When you do programming, this is what you need. First of all, you have to build some tree structure over there. You want to allow such tree structure to be built. The way we do this is by inheritance, okay? Polymorphism. What about the runtime? At the runtime, it's really important to see how the polymorphism and dynamic binding work together. Okay? Now, from the client's point of view, they are calling the same feature, for example, price. About how it is really computed, they don't care. It might be computed using attributes, it might be computed using some query, but because of uniform access principle, it makes no difference to the client. They shouldn't know. Okay? It's actually a good thing because they shouldn't be bothered. Okay, so that's why you got a uniform access over here. And as polymorphism, because you define the price feature at the top level. Let me just go back to the diagram over here. If you review this diagram over here, you can see that we define the price feature at the very, very top. And because of polymorphism, price is declared at the equipment's level. Any descendant classes of that can call this particular feature is available. Okay, that's polymorphism. And then what about dynamic binding? Dynamic binding is where you call the price feature, depending on what the particular equipment's type you're considering. If it is composite, you're going to run the loop. If it is base cases, then you're going to just do the unit prices, right? Just return the attribute value. Okay, so now let's say E of type equipments over here. If I say E.price, it might simply just return the unit price, like attribute value, if it's a disk drive. Disk drive is simply a disk drive is simply just over here. Okay, that's simply one of the base components. On the other hand, if I say E.price, also uniform access. E.price, if the dynamic type happens to be the composite components, in this case, it's going to run a loop, right? So that's dynamic binding. Guys, any question about composite before I move on? It's really important to see how this works because the next design pattern we'll see builds on top on this with a different example. Okay? You might find the patterns we talk about within these weeks applicable to your projects. I'll release a project on Wednesday. You'll see that. Okay? You got to decide which one to use. Okay, if no questions, I will simply just go on to visitor. Let me just make sure no slides left. Okay, we're done with composite. Let's now go to visitor. Let me just give you one small exercise right away, okay? Let's say this is your problem over here. Based on the composite pattern we just learned, I want you to think about how you can design classes to model structures. Structures like a key, the tree structures, hierarchies, for arithmetic expression like this. Let's say 341, 2, or 341 plus 2. Let's say we only got addition there, just to make things simple, okay? Think about it, and then let's go over your solution to see how close you are to the composite pattern, okay? How many classes would you have to create? How many? According to what we just learned from the composite pattern. We can enumerate them. What classes do you need? Dusan.
A composite class for addition, basic classes for one basic class for the integers 31 and 2, and extra class in general.
Okay, first of all, I can see a few things over here. So you're saying that you're going to create a class called 341? A class integer or constant. Oh, sorry, I misunderstood. Okay, of course. I thought you were going to create one class called 341 and another one called 2. That would be very naive, but you wouldn't do that. Good. Okay, so very good. So basically what we need is, we need one class that represents the base component over here, like a 341 or 2. Let's call it constant. Okay? And we got another one called addition. The addition class is like a composite. So now we also need another one called expression. Will be on the top. And also we got a composite class as we learned before. So this is what you have. Okay? And let me switch to iPad. Okay? So that's the composite pattern you have. If I give you, so this is just like another problem over there. Okay? So now you can see that over here, the composite over here, I'm just modifying that a little bit. So rather than having children, I simply say left and right, just for binary expression. Of course, in your design, you can feel free to change the way you want to structure your composite. I'm just giving you a different possibility. Okay, you got expression here at the top, you got constant, you got addition, you got composite. Okay? Of course, I missed the, there should be a client-supplier relationship over here. I'll try to add it. There should be one over here, okay? As we learned before, okay? That one should be there, okay? Okay, any question about this? Let's make sure we are on the same page before I move on. Now, let me tell you what the problems we are facing, the new problems. Before, we simply say we want to create the classes that will support to build the tree structure at the runtime. Now, that's more what we want to do. Now, let me present to you the problems. Okay, let me first talk about something called open-close principle. Open-close principle intuitively simply means the following. For any software artifacts you're building, there's always certain thing that's actually open for extension, which means you can always extend your software artifacts with some new features, new classes. What about close? Close simply means they should be closed for modification, which means this particular part of your software artifacts should be stable. You shouldn't change them. So now it goes back to MJ's question about how stable our tree structure should look like from the previous example. We'll see exactly like this, okay? Now, let's say for this particular problem over here, what does it really mean when we want to apply the open-close principle over here? That means we want to identify what's really open for this particular design and what is closed for this particular design, okay? Let's say for this, the one that's going to be closed is we have only constant and addition. We don't want to add any more arithmetic expression. That's it. The structure is really stable. The structure is what is closed. What about open? What can we extend over here? I'll show you. Extend simply means we can do various operations for this particular expression. Let me just go back to the slide over there. Let me just give you some example. Let's say this. Focus on 341 plus 2. Okay? What kind of operation can we do on that? Okay, let me give you some example here. Let's say you got 341 plus 2. Okay? Let's say the tree structure looks like something like this. You got addition there, and the addition has two children, which can be constant, and the constant is simply 341, and also 2, something like that. Okay? Let me make it even simpler. How about that? I can simply say it has constant 341 and 2. A very simple syntax tree. You might have seen this in 2001. So now this is the structure. So now we say that the structure is closed, which means they're stable. So now we want to say something about the openness of this particular structure. Well, about this particular problem we are dealing with. It's about operations we can apply. Okay? So now, let's think about what operation we can apply. Which means given a particular tree like this, what kind of operation can we apply to them? One, we can evaluate. In this case, if we evaluate this tree, it will be 343. Don't you agree? Okay, that's the one particular operation you can do. Okay, or you can say print prefix. Print prefix simply means I want to pre-print it, but in the way that it's going to correspond to a pre-order traversal of the tree, right? Which is going to be plus and then 341 and then 2. That's one way to pre-print it, right? Another operation here, what about print postfix? Well, just another operation over here. And then it's going to be the post-order traversal, right? Which is going to be 341, 2, and then plus, right? Just something that's different. One more. Type check. What does type check means? I want to know if this expression here makes sense, which means you're talking about addition. If you got addition here, if I have left-hand side being an integer and the right-hand side being also an integer, would that make sense? It makes sense. So type check, it just be true. I'll give you one thing where it wouldn't type check. For example, you might have plus over here, you have true and then 3. That one doesn't type check, does it? Right? You got a Boolean value there, you got an integer value on the right-hand side, you can add them up together. It does not type check. Okay? So now you can see that over here we talk about 4 different operations that we can support, at least 4. We might have something else. Let's say later on, we want to say, given any expression like this, we want to generate the corresponding assembly code, optimized, for example. That's another operation we may apply. Okay? You just get, so this is the open part for this particular design. You can keep adding new operation to your software design, but the structure there is always closed. There's certain part that's closed, also certain part that's open. So that's the open-close principle. Okay? That's the first time I talk about this principle here. Hopefully I'll try to talk a little bit more. Okay? Let's just go, any question about this illustration here? And I'll go over some slides. Okay, the structure over here is stable, it's closed. Yeah, just let me summarize this. And then the operation we want to support, they're open. You can just keep adding more operations. We want to have a design such that we can support such addition of new operations. Yes, question first.
I was wondering why this one that there's no kind of supply relationship directly between composite and expression one.
Oh, right. You're right. Over here, you know what? To be more precise, what I should have done was something like this. It's a very good question. So this is a particular one design, one possibility, or you can simply make, for example, T over here, right? In that case, I can simply get rid of this over here, and then addition would be simply just composite of T, and then I have the client supply over there. So this is just different possibility to show you, right? That's a good question. Yeah, but you're right, if I keep the original one, of course, I may draw a client supplier error over there, I may. Over here, I can say left, right. Okay, very good question. Yeah, I may do that, yes. But one thing to remember, you may get tons of client-supplier relationship in your classes. You don't necessarily have to show all of them every time. Show the ones that's important for the reader to understand your design. Yeah. Okay. Good. Okay. Let's now go over the open-close principle very quickly, and then we'll see how we can get to the visitor pattern. So software entities, classes, feature, they should be open for extension and closed for modification. So this is the principle for open-close principle. Okay. So what about in this particular example over here? So, okay, there's one more principle. So which means when you are extending the behavior of a system, that's the open part. When you are trying to extend the behavior, you may add new code, you may add new class or new features, but you should not modify the existing code, which means you should not go to the existing classes and modify some features over there. You can only add new ones. You shouldn't touch the existing code. So this should be the closing part. Okay? I'll try to illustrate this point a little bit more. This is more abstract at the principle level. Okay, let's say for our cases, we have an expression language, a very simple expression language there. So what's closed? We assume that the syntactic construct for the language is closed, which means it's stable. We don't tend to change them. Okay? What about open? Open means what can be extended. That means the operation we can support, right? You got pretty print, you got postfix, infix, prefix, type check, evaluates, or anything else, or code generation, right? You got lots of operation you can support, so that's unstable. Okay, so now, question for you. Let me just go back to, iPad first. This diagram is a little bit polluted, so why don't I simply just add a new diagram there, a new clean copy. And then I'll simply just add a new image there. And then the one I want to add is this, okay? This one here. So this is the composite pattern, okay? Now let's see what the question is for you. I want you to extend this composite pattern to support operations such as evaluates, pretty print, and type check. Okay, so this is a question for you. Now, how would you modify the design or to change that such that it's going to support all the operations? Well, of course, I'm going to show you, most likely you're going to have the solution that's going to modify this diagram in a particular way. But that's fine. But we'll just see what's your first intuition before we show you why it may not be so ideal. That's why we have a visitor pattern, right? Anyone would like to try? Don't be shy. Well, let's say just take one example. How would you support the evaluates? Let's say evaluate here. How would you support the evaluates feature for this particular design over here? I'll give you a little bit hints. Evaluates is a little bit like price for equipment, right? How would you evaluate a constant? Well, you just return its value, right? It can be 3, it can be 4. how would you evaluate an addition? You gotta evaluate the left-hand side recursively, and then reevaluate the right-hand side recursively, add them up together. So in some way, evaluate is like a price from the previous example. Given this hint, which may or may not be misleading, where would you put evaluates? Expression, I like that. I agree with you. Why don't we do that first? Well, actually, you don't have many choices, to be honest, unless you already know visit pattern, but that's another story. Evaluates over here. Okay, very good. If you put evaluate over here, that's going to be deferred, and then you're going to have evaluates over here. Also, you got evaluates over here, right? Two places. What about pretty print? Let's say print prefix. Print prefix. Where should we put it? In addition? Oh, okay. Let me just follow your design first. So what you're suggesting is we put print prefix only in the addition, right? Why don't we try? Print prefix. The problem for this is, how can I print prefix for constant then? Right, you're missing that, right? We know, actually, let's learn from this. If I put the print prefix feature in the addition class only, that means it's only available on the descendant classes of addition, including itself. It wouldn't be including constant. So constant has no print prefix available, right? So do some, change that, where should we put them? I agree. Print prefix. Okay, and then we also got print prefix over here. And print postfix is pretty much the same, also expression. Let's do one more. Type check. Where should we put type check? In constant? Oh, I like that, because in this case, you kind of give the opposite of what Duzan said, right? If you put a type check over here, let's say type check. Okay, that means, okay, first of all, if I say type check number 3, should I return true or false? True, right? Because numbers, wow, there's not much you can say. As long as you spell the numbers correctly, they should type check. So any numbers by default should give you true for their type checking. But now, according to your design, if type check is only available in constant, can you type check 3 plus 4? I agree with you. Okay, conceptually, yes, but think about this. If I say 3 plus 4, at the upper level, you still got a plus, right? Which means for your program to view this input over here, it doesn't view it as 3 and 4 separately. It views only an addition, right? But the addition itself does not have the type check feature, right? You can see what's going on here, right? Okay, so what should we do? What should we do to fix it? Expression? Right, good. Type check over here. And then type check. Okay, type check. Okay, now we're pretty much done. So now let's say a little bit more general. Imagine that later on, if I got, let's say just do one more, how about that? You know, just keep doing. I want to make the point very explicit to you. What about I use green? Let's say we got another feature to support called code generation. Let's say we want to generate the assembly code for the expression. For example, assembly code for constants, assembly code for addition. In this case, what should we do? Where should we put this generate feature? Where should we put it? Should we put it in addition only? Or should we put it in constant only? Or should we put it somewhere? Or should we put it in composite? Generates. Okay? Gilbert. Expression? Yeah, I agree. So we should put it in the expression, right? So basically, every feature you want to support for expression should go to the superclass. It seems to be the best we can do for the composite pattern. Okay? Okay, after this, I'm gonna tell you why this may not be so ideal, okay? So now I'm gonna put also generate over here. Generates, generate, also generates. Okay, so now, what's wrong or what's not so good about this design here? First of all, your design does not really smell because after all, you really have to design your features about evaluate, pretty print, type check, and generate somewhere. We just choose to put the features in the individual classes and put their defer versions in the expression class, right? So this design does not smell, okay? It's okay. However, I want you to think about what's the, let me not say definition. What's the purpose of a class? What's the purpose of a class, just in general? Your Java class or your C++ class, Python class, iPhone class? What's really the very purpose of a class? For example, yeah, go ahead. Something unique? Not necessarily. Not necessarily. Generate output? That's more about runtime, right? I'm just talking about design. So, for example, let's say, yeah, let me give you one example and then I will take your question. Okay. Let's say, why would we have two classes? One is called students, the other one is called stack. They're different classes, right? Why don't we just collapse them into a single class? Because they got different functionalities. So somehow, let's say in the student class, we got something called register. In the stack class, we got something called push and pop. Are these two operations really related to any sense? They don't, right? Register, push and pop. No. Register only belongs to the concept of students, and push and pop only belong to the concept of stack. So they should not belong to the same class, right? Now, when you look at what we got over here, I'll just choose two features over here, just for this particular example. Let's say over here, I want you to look at, how about yellow? Generates and evaluates. So these two features over here, they are actually not really related. One is about giving you the result for the evaluation. The other one is to generate a target language which is going to be optimized. So they are actually two different processing jobs. But now we try to group them together under the same class. So we are basically mixing concept together. For our convenience, we simply put every operation in the same class over here, but we miss the very, very purpose for class, which means we should only group relevant concept together. If you try to mix too many concepts together, it's pretty much like you have a single class with push and pop, DQ and InQ. That doesn't make sense, right? Can everybody see the point? Or in more general, you can see over here, if I try to add more operation, let's say operation 1, operation 2, up to operation 100, according to the way we accumulate our classes, what I will get is I will get operation 1, operation 2, up to operation 100. And these operations might just be completely random or ad hoc. They simply have nothing to do with each other, but we group them into the same class, hoping that they will be related to each other, but they don't. So now your class is simply a placeholder. It's not really a class anymore. It's simply just a collection of features rather than a collection of related features. Okay? That's my point. And then, now what? Well, we're going to improve this design. Yes, go ahead. So the class, yeah, okay, there are many ways to talk about a class. So one aspect I'm focusing on right now is to say a class should really group only relevant concepts together. If you find that there are actually two very different concepts together in your class, you should separate them into different classes. Class simply means classification, right? You cannot classify push and pop into the same category as DQ and InQ. They belong to different concepts. That's why they shouldn't be in the same class. Right? Guys, any question about this? That's a little bit more abstract, but that's why we are doing design. We are trying to be critical. Okay? So, as far as the implementation is concerned, this very initial design is not too bad because your code does not smell. You try to define every operation at a single place, that's fine. However, as far as the design is concerned, this violates the very principle about what a class is to serve us. Okay? It's not good. Okay? Okay, not so good. So here, it violates also the single choice principle somehow. Let's see, in this way. Okay, let me just ask you this. Now, let's go back to this particular design over here. Let's say this. If I want to say, now I no longer want to support the print prefix function, the print prefix feature, what would I do? Let's say I do not want to support this feature anymore. Let's say not support anymore. How many places do I need to change? One? If you had to change in more than one places, then you're in trouble. How many places you got to change? Yes? 3? Which 3? Exactly. These are the expression constant addition. These correspond to all the descendant classes of expression, including itself. But now, imagine that we got a very complicated language structure. We got 100 different descendant classes for expression. In that case, you got to change 100 places to delete them, right? To add one or to delete one, even though your code doesn't smell, but it violates the single choice principle, okay? Because you got to change in more than one places, okay? Okay, so now, also about cohesion. Cohesion is exactly the point I talk about. Cohesion means in a single class, everything should be related to each other. They shouldn't be conceptually separate, okay? They should be related to each other, okay? Okay, so now let me see this. Guys, what's the time right now? Time really flies. 6:49? Oh, okay. How about this? 1 minute left. Since I cannot go to visitor today, but I would suggest, here's the thing. Let me stop the recording first.